All right, so today we're looking at 3.2 polynomial functions and their graphs. So we here have the definition of a polynomial function, which says let n be a non-negative integer and let a sub n x to the n, and then continuing on until we get a sub 0, which is our constant, be real numbers where a sub n cannot equal 0. So the function defined by f of x equals that expression is called a polynomial function of degree n. The number a sub n is the coefficient of the variable to the highest power. It's called the leading coefficient. So here's what that's saying. Once we take a polynomial function, so anything to the second power, looking at our quadratics, or going to the sixth power, as long as it's written in standard form with only x's in the function, then that is considered a function if we have smooth continuous graphs, which we can see here below. So polynomial functions of degree 2 or higher have graphs that are smooth and continuous. By smooth, we mean that the graphs contain only round curves with no sharp corners. By continuous, we mean that the graphs have no breaks. So there's examples of what makes a graph a polynomial function and what does not here. The one thing to make sure, as long as you can draw the curve without lifting your pencil, then it's a polynomial function. So we're going to break this up into different parts when we want to graph our polynomial function. The first thing we're going to look at is in behavior. Within behavior, we can think about this the same as when we look at our odd and our even functions. So remember, an odd function, usually we're looking at a line. Okay, or an even function, we look at our parabolas, whether they're facing up or down. Okay. So if you have an odd degree polynomial function and your a sub 0 or your leading coefficient is greater than 0, which means it's positive, that means that you're going to have a function, let's say, with kind of like a positive slope. And behavior is down, up. Okay, and then if it's negative, think about it as having like a negative slope. Okay, and I just draw that two parts with the arrows and break it apart. So for even, if it's positive, both of your ends are going to be facing up. And if it's negative, they're both going to be facing down. All right, so looking at these two examples, use the leading coefficient test to determine the end behavior of the graph of. So look at the first one. F of x equals x cubed plus 3x squared minus x minus 3. It's in standard form already. And our degree is 3, because that's our highest exponent. And then our a sub n, or a sub 3, I guess is actually what that would be, which is our leading coefficient, is 1. Okay. And since that's positive, I'm going to go ahead and write that down. All right, so degree 3 means that they're going opposite directions. And since it's positive, we're going to start down and go up. Okay. Looking at the second one, f of x equals negative 4x cubed times the quantity x minus 1 squared times the quantity x plus 5. Here's, you have to be careful because we really need to multiply this all out to figure out our degree, but we can kind of do a shortcut here. Let's just look at each of our exponents. So we have 3, 2, and 1, and we're going to add those all up, and we get 6. And then our leading coefficient, if we look at these first terms, we have x and x, so no matter how we multiply those, we're just going to have a 1 in front. And then we have negative 4. So 1 times negative 4 is negative 4, which is obviously negative. So even means they're facing the same direction. And since our leading coefficient is negative, it means they're both going to be facing down. All right, the next thing we find is the zeros of a polynomial function, or the roots, or the solutions. So the way we find these is by solving. Okay, set the function equal to 0 and solve. We usually do this using factoring. So let's go ahead and do this first example. We have f of x equals x cubed plus 3x squared minus x minus 3. So I'm going to set this function equal to 0. And since there's 4 terms, we're going to factor by grouping. So this gives us x squared times the quantity x plus 3. Factor out a -1. And again, we're left with x plus 3. So 0 equals the quantity of x plus 3 times the quantity x squared minus 1. We can factor x squared minus 1 further. So we can get 0 equals the quantity of x plus 3 times the quantity x plus 1 times x minus 1. So now that we have this factored, we can say x equals -3, x equals -1, and x equals +1. Because if we set each of those binomials equal to 0 and solve, that is what we would get. So now I want you to try this second function, -x⁴ plus 4x cubed minus 4x squared, and see what those x-intercepts or those zeros would be. All right, so once we know the number of zeros, okay, we're going to use this idea of multiplicities to determine what happens to our graph at that x-intercept. Okay. So when we do this, if we look at the example you guys just tried, then we get something that gives us multiplicities, which actually, let's see here. I'm going to make this up, but I think that you're going to get -x squared times the quantity x minus 2 squared. Okay. So notice that each factor occurs twice. So in factoring the equation for the polynomial function f, if the same factor x minus r occurs k times, but not k plus 1 times, we call r a 0th multiplicity k. So here's what that means. We could rewrite this as -x times x minus 2 times x minus 2. Okay. That tells us that when we're looking at our intercepts, we get x equals 0, x equals 0, x equals 2, x equals 2. So the multiplicity simply says how many times does that x-intercept occur? So we can say for 0, x equals 0, that our multiplicity is 2, because it occurs twice. For x equals 2, here our multiplicity is again 2, because it occurs twice. So multiplicity provides another connection between zeros and graphs, because like I said earlier, it tells us what happens at that x-axis. Does it touch and go through, or does it bounce back and turn around? So if r is a 0 of even multiplicity, then the graph touches the x-axis and bounces back. The easiest way to remember this, even, is going to bounce back, kind of like a parabola does, depending on where it's at. Okay. And then if it's odd, it's going to cross through, like a line. Okay. All right, so if we look at this example, find the zeros if f of x equals 1/2 times the quantity x plus 1 times the quantity 2x minus 3 squared, and give the multiplicity of each 0, then state whether the graph crosses the x-axis or touches the x-axis and turns around. All right, so I'm going to take just the parentheses part. So we have x plus 1. I'm going to set that equal to 0. And then we have the quantity 2x minus 3 squared equals 0. Well, this tells us that x equals -1, and that would be considered our 0. Okay. Now look back at your exponent. There isn't an exponent, so here our multiplicity would just be 1, because it only occurs once. And since that's odd, that means it's going to cross through. Okay. So now look at 2x minus 3 squared equals 0. So I'm going to ignore the squared for right now. If we'll just look at this inside, 2x minus 3 equals 0. Add the 3 to the other side, then divide by 2. That tells us that x equals 3 halves. Our multiplicity is going to match our exponent, which here is 2. And since that's even, it's going to touch and bounce back. Or turn around, however you want to write it. Okay. So now I want you to try the second example. And make sure you state what the 0 is, the multiplicity, and then what the behavior is at the x-axis. All right, so once you know those, then we can look at the intermediate value theorem to see what happens between two x values and two zeros. We're going to come back to this and talk about it after we've graphed one. And then lastly, before we start graphing, we have turning points of polynomial functions. The graph changes directions from increasing and decreasing or vice versa is called a turning point. If f is a polynomial of degree n, then the graph should turn at most n minus 1 times. Okay. All right, so then we have our strategies. We kind of already talked about this. So the first one, we want to figure out what our end behavior is. The second one, we want to find our x-intercepts based off of the zeros and determine what happens at each of them. And then we're going to find the y-intercept by computing f of 0. And lastly, if we want, we can use symmetry, if it's a y-axis symmetry or origin, to help determine what's happening on both sides of the graph. That sometimes helps us. We'll look at an example when that does. All right. So we have two examples. And let's just do this. Let's see here. Let's do the first one. Okay. So without the use of a graphing calculator, graph the function x to the fourth minus 2x squared plus 1. So first things first, we want to look at our end behavior. So our degree is 4. And our a sub 4, or our leading coefficient, is 1. So our end behavior for even positive is up, up. Okay. Now we want to find our x-intercepts. So I'm going to set this expression equal to 0. Okay, so 0 equals. So this can actually factor. So our factors of 1 that add to be -2 are -1 and -1. But then we have to be careful here. So x to the fourth. So instead of writing just x, this is going to become x squared minus 1. And I'm going to actually write this out twice, x squared minus 1. Because x squared minus 1, this can factor further and give us x plus 1 times x minus 1, x plus 1, x minus 1, which we can rewrite as the quantity of x plus 1 squared times the quantity of x minus 1 squared. So now we have our two zeros of x equals -1 and x equals +1. Both of them have a multiplicity of 2 because they're both to the second power, which means they're both going to touch and bounce back. So I'm just going to write BB for both of those. Okay. So our third step is to find our y-intercept, which means we're finding f of 0. So if I plug that in, what's nice about this one is since it's in standard form, we can just look at our constant at the end. So our y-intercept equals 1. And then lastly, we can look at our symmetry. Okay. here we can say that we have an even function. And the reason why is if you look at your exponents, all of them are even. So that means that this is symmetric across the y-axis. All right, so I'm going to go ahead and plot what we know. We know we have an x-intercept at -1 and +1. And we have a y-intercept at 1. So I always recommend you start on the far left of this graph. Okay, so I'm going to start on the left, and we know we're starting at the top because of our end behavior. So we're starting at the top, coming down to our x-intercept, and then we're bouncing back. So we're going to bounce back up. We have to go through that y-intercept, but then we're going to have to turn around to go back to that second x-intercept. So at x equals 1, we're going to bounce back. I'm going to curve that back up. And there is your function. So now I want you to try this second example. At least try to answer these 4 parts: end behavior, zeros, y-intercept, and the symmetry. Okay, and try sketching the graph and see what you get for this last function.